Rain is falling with a velocity of, let us say, 20 meters per second at an angle of 30 degrees with the vertical. Now you're coming along in a bicycle moving at, let us say, 10 meters per second. What is the angle that the rain makes with the vertical in your frame of reference? So what does frame of reference mean? Frame of reference simply means as measured by you. A person standing on the ground says the rain is coming down at 30 degrees. So we say in the frame of reference of this person, it's coming down at 30 degrees. And the question is, in the cyclist frame of reference, what angle does the rain make with the vertical? Consider two frames of reference. There is a person A standing on the ground. This person has her own measuring instruments, for instance, survey instruments, clocks, etc. And using these, he measures the velocities of various objects in the world. At the same time, there is another person who is in a moving car. I'll just represent the car by this box. This person B is in a car which is moving with a velocity of u. Now she also has her own measuring instruments, survey instruments, clocks, etc. Now she also looks out into the world and measures the positions, displacements, velocities and accelerations of various objects. Let us say A and B are both looking at one such object, let's say a bird. Now A looks at the bird and says the velocity of the bird is v. At the same time, B looks at the bird, makes her own measurements, and then says at the same instant the velocity of the bird is v prime, a different vector. So our job is to find now what is the connection between these two vectors. If I know one of them, can I calculate the other? V is the velocity which is measured in A's frame of reference. That's how you say it. And v prime is the velocity of the bird as measured in B's frame of reference. When you say in B's frame of reference, it does not mean that the bird is in the car. It just means as measured by B using measuring instruments which are at rest with respect to her. In fact, A has his own coordinate system, a z-axis, a y-axis and an x-axis, x, y and z, and in this coordinate system he measures the positions of all the objects in the world, including the bird. In the meantime, B also has her own coordinate system, and for simplicity today we'll take both the systems as being oriented so that their axes are parallel to each other. So this is B's z-axis, which to distinguish from A, we are going to call it z prime. This is B's x-axis. So whatever coordinate she measures, she's going to call it x prime. And this is the y prime axis. So whereas A will say the position of the bird is given by the coordinates x, y, z, B will claim at the same instant the bird's coordinates are x prime, y prime, z prime. It's quite obvious that these numbers are going to be different. Before I give you a formal proof of the relationship between V and V prime, let us just use a little bit of common sense and try to guess what it might be. Let's say you're in a car and you're moving with the velocity u. And what do you see? With respect to you, the car is at rest. You look out the window and what do you see? You see the tree moving with a velocity minus u. At the same time, observer A standing on the ground will claim that the tree is at rest, the velocity of the building is 0, the velocity of that mountain is 0, and the velocity of the ground is 0. So you can see when A measures a velocity of 0, to get the velocity as measured by B, you need to add to this minus u. So you might guess that if A measures the velocity of the bird as v, then B, who is in the moving car, might measure the velocity as v prime, which is v minus u. She might just add an extra minus u to all the velocities measured by A to get the velocities as seen by her. We will now show this formally. So here we have A's frame of reference, which is represented by A's coordinate system, and this is at rest with the ground. And here's B's frame of reference, which is moving with the car. Let's call A the stationary frame and B the moving frame, although from B's point of view, it is A that is moving. So we might ask, who is really stationary and who is really moving? That question we will answer in a subsequent video. For now, just to distinguish between the two, I'm going to call A stationary and B the moving frame. Now they both look at this bird. Let's draw the position vector of the bird as seen by each one at some instant of time. So at some instant of time, the bird is here and B is here. Remember, B is also moving with respect to A, and so is the bird. So A will say the position of the bird is given by this position vector, which we shall call R. At the same instant of time, B will claim that the position vector of the same bird is this vector. Let's call that R prime. We are going to need one more vector, and that's the position of B with respect to A. So this is a vector that gives us the position of the origin of B's coordinate system as measured by A. Let's call this RO, meaning the position vector of the origin of B's coordinate system. Now as time goes on, remember the bird is moving, so R is changing, R prime is changing, and since the car is moving, RO is also changing. But at every instant of time, this relationship will hold. If you look at this triangle, you can see that if I start here and end here, that is vector R, it's going to be equal to RO plus R prime. RO plus R prime. Now this relationship is going to hold at every instant of time. As the bird moves and as the car moves, R, the position vector of the bird, as seen by A, is going to be related to the position vector R prime of the bird as seen by B. They are connected by this relationship. Let's differentiate both sides with respect to time. After all three vectors are changing with time. They are functions of time. So we get dr by dt is equal to dro by dt plus dr prime by dt. What is dr by dt? It's the velocity of the bird as seen by observer A at this instant of time. And that's equal to dro by dt. What is dro by dt? It's the velocity of the car. It's the velocity of the origin of B's coordinate system. But B's coordinate system is at rest with respect to the car. It's moving with the car. So this is the velocity of the car, which we previously called u. Of course, u is changing with time. We are not claiming that u is constant. We are just looking at things at one instant of time. Plus dr prime by dt, it's the velocity of the bird as seen by B, the moving observer. As promised, the velocity seen by the moving observer is the velocity seen by the stationary observer minus the velocity of the car. How do we use this to solve our rain problem? Let's go back to the rain problem. This was the problem. Rain is coming down at an angle of 30 degrees with the vertical, and a cyclist is moving at 10 meters per second. What are the two frames of reference? Here we have observer A standing on the ground, and from his point of view, the rain is coming down at 30 degrees with a velocity of 20 meters per second. And with respect to him, the cyclist is moving at 10 meters per second. The other frame, the moving frame, is the cyclist frame. The question is, what angle does the rain make with the vertical in the cyclist frame? In the cyclist frame, the velocity of the rain is v prime. Now, as seen by the person standing on the ground, the velocity of the rain is v. And we know the relationship is v prime is v minus u, u being the velocity of the moving observer. Very well. In order to do vector addition or subtraction or anything to do with vectors, it's best to set up a coordinate system and work with components. So let us choose our usual x-axis pointing to the right and y-axis pointing vertically up. In that case, the velocity of the rain is 20 cos 30 in the negative y direction. So minus 20 cos 30 in the j cap direction and 20 sin 30 in the x direction. 20 sin 30 in the I cap direction. Again, if you look at the rain's velocity, it makes an angle of 30 degrees with the negative y direction. So 20 cos 30 is the component in the negative y direction, and 20 sin 30 is the component in the positive x direction. So v becomes 10 I cap minus 10 root 3 j cap. The velocity u of the moving frame in our coordinate system is 10 I cap. So let's go plug it in. V prime is the velocity of the rain as seen by the moving observer is 10I minus 10 root 3 j, which is v, minus 10I. So what do I get? 10 minus 10 becomes 0 minus 10 root 3 j cap. The I component is 0. So in this one's frame, the rain appears to be coming down vertically. It has no horizontal component. Does that make sense? Of course it does. Think about it. Supposing you are running at 10 meters per second in this direction. Well, assuming you're as fast as Usain Bolt, let's say you're running at 10 meters per second in this direction. And next to you, a cyclist is also moving at 10 meters per second. So from your point of view, the cyclist is at rest. In the same way, the rain has a horizontal component of 10I and you also have a velocity of 10I. So from your point of view, the rain's horizontal component is 0. It appears to be coming down vertically. Thank you.